Hello, and welcome to the video lecture for topic 4, Lewis structures. So to begin, we've seen a few different ways that we can represent an organic molecule and contribute all the structural information we need to. So we've seen full skeletal formulas or structural formulas where we draw every atom and every bond. We've seen condensed structures where we condense groups of atoms together and we can eliminate the majority of bonds in the molecule. We've also seen line structures, or what are known as skeletal formulas, where we keep most of the bonds. We eliminate any hydrogen atoms that are bonded to carbon. We eliminate the bond between that hydrogen atom and the carbon it's bonded to. We keep all of our carbon-carbon bonds, but we don't explicitly draw the carbon atoms, right? So we've seen these different ways. A Lewis structure is yet another way or another convention for representing an organic molecule, and the use of a Lewis structure is going to become very important to us as we move through this semester and on into next semester, in that it explicitly shows all of the electrons that are in the valence shell but not participating in bonding. And this becomes important when we get into topics such as resonance, and this becomes even more important when we get into arrow pushing mechanisms. We have to show all electrons when we do our arrow pushing mechanisms, and in fact you will be most often drawing some version of a Lewis dot structure or a Lewis structure for most of the times that you represent organic molecules, both this semester and next semester. So let's take a look at how it is that we take one of the structures we've seen before. We're primarily going to focus on structural formulas and line structures. We won't work with condensed structures during this topic. But how we can convert what we've seen before in terms of structural formulas and line structures into a Lewis dot structure or a Lewis structure. So a Lewis structure really begins by drawing a full structural formula or the line structure, and we follow our standard rules for bonding. So just as a quick review, we know that carbon forms 4 bonds. We have hydrogen or halogen will form 1 bond, right? Nitrogen, phosphorus, and I'm going to throw it in here just so that you're aware, and boron all form 3 bonds. Of course, we know that there are some special circumstances for phosphorus, but we're not going to get into that right now. For oxygen or sulfur, we are going to just use our standard 2 bonds. Okay, so these are the bonding rules we need to keep in mind. Carbon forms 4, hydrogen and halogens typically form 1, nitrogen, phosphorus, boron will form 3, and oxygen and sulfur will form 2 bonds. So next, to be able to do a good Lewis structure, we need to have in our minds the number of valence electrons that each of these atoms will typically bring to bear in the molecule. So just going from smallest number to highest number, hydrogen has 1 valence electron. So these are valence electrons. So hydrogen has 1, boron has 3, carbon has 4. For nitrogen and phosphorus, we have 5 valence electrons. Oxygen and sulfur, we have 6. And then halogens have 7 valence electrons. Okay, so we're going to keep all of these things in mind when we convert a structural formula to a Lewis structure. So let us go ahead and take a look at the last couple of rules that we're going to need to keep in mind. Right, so we're going to keep our standard bonding rules, our number of valence electrons. We're going to keep in mind that when converting or when we're making a Lewis dot structure, we're always going to subtract all the bonding electrons, subtract our bonding electrons, right? So that's our third thing that we need to remember. And finally, the last thing we're going to need to keep in mind is distribute extra or remaining electrons, right? So these are the four things we're going to keep in mind. So let's see how we apply this. Let's take an example, and I'm just going to draw here a structural formula real quick. We'll put in a ketone. We will put in an alkene. And we'll add in a halogen. So this is a structural formula. In order for it to become a Lewis dot structure, which is what we're aiming to get towards here, we need to account for all of the valence electrons that are currently missing. Right now, all we're dealing with are bonding electrons. We need to deal with any non-bonding valence electrons as well. And so we're going to keep our systems in mind here, and let's go ahead and do this. So the first thing we need to do is to figure out how many electrons we have and how many electrons we have, so to speak, extra. So we begin by taking the number of each type of atom and multiplying it by the number of valence electrons that it has. So for carbon, we have 4 carbon atoms. Each one contributes 4 valence electrons for a total of 16. For hydrogens, we have 5 hydrogen atoms in our molecule. Each contributes 1 valence electron for a total of 5. We have 1 oxygen, which contributes 6 valence electrons. And we have 1 chlorine, which contributes 7 valence electrons. So 16 plus 5 plus 6 plus 7, if I add those all together, I have a total of 34 valence electrons. Step 1. So I have now counted up all the valence electrons contributed by all of the atoms in this molecule. The next thing I want to do is count up how many of those electrons are being used for bonding. So now we've moved on to this step. We know our bonding patterns to make our structural formula. We know the number of valence electrons each element and atom will contribute in order to give us the total electrons that should appear in our structure. Next, we're going to determine how many electrons are already being used for bonding. So we can simply count each covalent bond. 1, 2, 3, 4. A double bond counts for 2, so that's 5 and 6, 7, 8, 9, 10, 11, 12. So that means I have 12 bonds. Each bond has 2 electrons in it, which means that I have 24 electrons that are being used in bonding. Now we do this step, which is subtract all of our bonding electrons. So we have 34 valence electrons total. 24 valence electrons are used for bonding. That means we have 10 electrons that we still need to account for in our structure. That comes down to 5 lone pairs, or 5 non-bonding pairs of electrons. We always want electrons in pairs unless we're doing radical chemistry, which we won't see until the very end, or nearly the very end of this semester. And so all of our electrons need to be paired, so we're going to divide this number by 2, which gives us 5 non-bonding pairs of electrons. Non-bonding pairs, right? Non-bonding pairs are typically called lone pairs. They are abbreviated letter L, letter P, and so this will probably be the last time you see me use the convention non-bonding. I will move to lone pair from now on. So we need to account for all of these 5 non-bonding pairs of electrons. And we do that by looking at the atoms whose valence electrons doesn't match their number of bonds, so to speak. So oxygen, we have one oxygen, right? It is only using 2 of its valence electrons to form this bond, right? This double bond. So the oxygen provides 1 electron to each bond, and the carbon atom provides 1 electron to each bond. So that means oxygen, as it's displayed here, is only using 2 of its valence electrons. And there should be 4 more valence electrons on that element, or on that atom, which means we can take 2 of these pairs, 1 pair goes there, 1 pair somewhere else next to the atom, and what we see now is that we have the correct number of valence electrons around oxygen. 1 from one of the bonds, 2nd from the other bond, 4 from our 2 lone pairs, for a total of 6 valence electrons around oxygen, and it's a happy atom in our Lewis structure. Similarly, we know that halogens should have 7 valence electrons. It's only currently participating in 1 bond, which means there are 6 valence electrons which are not clearly displayed here. And so we can take care of that by putting 3 lone pairs around our chlorine atom. We now have 6 non-bonding electrons, 1 bonding valence electron. That gives us the 7 valence electrons contributed by chlorine. For a full octet, we need 8, and that 8th electron comes from the valence electron that carbon is sharing in this bond. Okay, so there's our first example. And really, the only difference between a Lewis structure and a structural formula is that the Lewis structure explicitly shows every valence electron by adding in non-bonding pairs onto any atom that should have them. So the next question you should be asking yourself is, but wait, Sam, what happens if I form an octet on an atom, but it violates my accepting bonding patterns? And that's a great question. So next we're going to take a look at an example where that occurs. Okay, so an example where we violate the octet rule, and how do we handle it? So let's start off with this molecule here. Nitromethane. Okay, nitromethane is common in racing fuel, if you race cars or if you race motorcycles. It's also a common reagent in organic chemistry and a common solvent for organic chemistry as well. And it happens to be a perfect example for us of how do we treat violations to our bonding rules in a Lewis structure. All right. So we're going to begin with the same steps. First, we're just going to determine the total number of valence electrons in the molecule. And so we have 1 carbon atom, and that's going to be 1 times 4. We have 3 hydrogens. That's going to be 3 times 1 valence electron. We have 1 nitrogen, which is going to be 1 times 5 valence electrons, and we have 2 oxygens. Whoops, not 16. Pardon me. So we have 2 oxygen atoms, and each will contribute 6 valence electrons. So 4 plus 3 plus 5 plus 12 comes to a total of, we have 24 valence electrons that we need to account for. Okay? So as we see it right now, what we have is 1, 2, 3, 4, 5, 6 bonds. So if I have 6 bonds, right, at 2 electrons each, that's going to give me 12 electrons bonding. Remember, we have 24 valence electrons. That means we have 12 electrons that we need to account for, or 6 pairs that we need to assign. Carbon and hydrogen are satisfying their neutral bonding rules currently, right? Each hydrogen has 1 bond to it. The carbon has 4 bonds to it. Nitrogen appears to be satisfying its bonding rule in that we have 3 bonds to our nitrogen atom. And then oxygen is the one that's really deficient, where we have only 1 bond to each of our oxygen atoms, where it wants to have 2. So let's begin assigning our 6 pairs. Based on what we see here, we should put 3 lone pairs onto this oxygen atom, right? And so now it has a full octet. If we put 3 lone pairs onto the other oxygen atom, we've used up all 6 pairs that we still need to account for, and we now have a good distribution. The only issue being that nitrogen doesn't have a bonding pair, right? And so we'll ultimately need to see how to account for that. So let's begin by dealing with our 2 oxygen atoms. We know that it doesn't obey the bonding pattern, and it does have the right set of octet, the right number of electrons to have a full octet. 1, 2, 3, 4, 5, 6, and 2 more from the bond to nitrogen. That makes 8, and that's happening in both situations. So what we need to do now is account for its formal charge. And to determine its formal charge, we're going to use a simple equation: valence electrons minus the number of bonds plus the number of non-bonding electrons. Now this is not how many lone pairs, it's how many non-bonding electrons. So each lone pair has 2 in it, and we'll see that applied here in just a moment, is going to equal the formal charge of the atom. And we should go through this process for each atom that violates our standard bonding rules. We'll begin with this oxygen. We have 6 valence electrons minus 1 bond plus 6 non-bonding electrons. 6 minus 7 is -1. For this oxygen, we have the same scenario. 6 valence electrons minus 1 plus 6 bonding electrons, non-bonding electrons. Again, we have 6 minus 7 will equal -1. We also see that nitrogen is violating its valence pattern. We only have 6 valence electrons around nitrogen right now, even though we'd like to have a full octet for it to be neutral. And so to account for nitrogen, it contributes 5 valence electrons. It has 3 bonds, right? And we're going to add to that 3 bonds the number of non-bonding electrons, which is currently 0. So 5 minus 3 should have a charge of +2. All right. So next we're going to go ahead and put each of these formal charges onto the atoms they correspond to. So we have a negative on the oxygen, we have a negative on the other oxygen, and we have a +2 on the nitrogen. Now, whenever possible, we want to reduce the total number of formal charges. Right now we have 1, 2, and depending on how you look at it, either 3 or 4, right? So that's a lot. And one of the ways that we can reduce in a situation like this, where we have a negative charge and a positive charge adjacent to each other, is to use one of these non-bonding pairs at the negative site to create a new bond to the atom that has a very high positive charge. So what we would do is we would erase this lone pair off of the oxygen and create a nitrogen-oxygen double bond. Let's take a look at oxygen now and reapply this rule. Now we have 6 valence electrons minus 2 bonds plus 4 non-bonding electrons. That now gives us a formal charge of 0. And so we can erase this negative charge now. If we redo our calculation for nitrogen, 5 valence electrons minus 4 bonds plus 0 non-bonding electrons simplifies to 5 minus 4, which gives us a plus 1 charge. So now instead of a plus 2 on nitrogen, we have a plus 1. And when the formal charge is 1, whether it's negative 1 or positive 1, we don't write the number, we just put the sign. And I like to put a circle around it. About half the people out there do, half the people out there don't. I find that circling your charge does a good job of highlighting it so it catches the eye of whoever's reading the structure that you're drawing, and just makes it clear that the formal charge is there and it's not something that sort of there, half erased, but the circle around it really brings it home. So there you go. This little simple rule, valence electrons minus the number of bonds plus the number of non-bonding electrons, not the number of lone pairs, right? Number of non-bonding electrons is really good to calculate your formal charge. And you'll need to calculate a formal charge anytime you break our common bonding rules, right? Or you fail to end up with an octet around one of your atoms. All right. So to wrap up this video lecture, I'm going to give you a set of general rules that you can count on most of the time for determining formal charges just by quickly looking at the atoms. Okay, so our general rules for formal charges. I'm going to cover the main elements that we encounter most here in organic chemistry, and these general rules will be good for the overwhelming majority of situations you encounter both this semester and next semester. So we'll start off with carbon. Right? If I have 4 bonds to carbon, no lone pairs, my formal charge is 0. If I have 3 bonds to carbon, no lone pair, my formal charge is plus 1. And if I have 3 bonds to carbon and I have 1 lone pair, my formal charge will be minus 1. For nitrogen, if I have 3 bonds to nitrogen, 1 lone pair, the formal charge is 0. If I have 2 bonds to nitrogen and 2 lone pairs, my formal charge will be negative 1. If I have 4 bonds to nitrogen, 0 lone pairs, my formal charge will be plus 1. For oxygen, if we have 2 bonds to oxygen, 2 lone pairs on the atom, we have a formal charge of 0. If I have 3 bonds to oxygen and I have 1 lone pair on the atom, I will have a formal charge of plus 1. And finally, if I have 1 bond to oxygen and I have 3 lone pairs, my formal charge will be negative 1. For hydrogen, if I have 1 bond to hydrogen, 0 lone pairs, my formal charge will be 0. If I have no bonds to hydrogen, no lone pairs on it, my formal charge is plus 1. And finally, if I have no bonds to hydrogen and 1 lone pair, my formal charge will be negative 1. And finally, let's take a look at the halogens. So this is going to be any of the halogens. Okay, if I have 1 bond to the halogen, I have 3 lone pairs on the atom, we have a formal charge of 0. If I have 2 bonds to the atom, to the halogen atom, and 2 lone pairs, I will have a formal charge of plus 1. And if I have no bonds to the halogen, 4 lone pairs, the formal charge will be negative 1. And so this table that I've put up here, this will cover the overwhelming majority, as I've said, of the situations you'll encounter with the most common elements we interact with in organic chemistry. All right, as always, if you have any questions, please bring them up in lecture, conference, or stop by for office hours, or make a Google Calendar appointment. Thank you very much.